Hilbert spaces. If you're not sure what they are, you're in good company. As the legend goes, the great mathematician David Hilbert once entered a lecture hall. The speaker that day was fellow math giant John von Neumann. The topic? Hilbert spaces. At the end of the lecture, a confused Hilbert raised his hand to ask just one question. What is a Hilbert space? I love this tale. It would be like if Pythagoras asked about the Pythagorean theorem. While the story is likely just a legend, it amusingly captures the importance that both of these figures played in the development of Hilbert spaces, with Hilbert laying much of the groundwork and von Neumann finishing it off by giving the first complete definition of them. These spaces then quickly became useful in areas like quantum mechanics, the physics of heat transfer, and even modeling sound waves. Admittedly, when I first encountered Hilbert spaces, they were a bit intimidating. But here, you will see that they are really just a natural generalization of the spaces we encounter in high school geometry. We begin with a humble vector, an arrow in the two-dimensional plane. By choosing a specific coordinate system, we can specify the location of this vector with just two numbers. How many steps we need to take in the x direction, plus how many steps in the y direction. Although this is generally the standard coordinate system we use, there's nothing that prevents us from using another one. We can just as easily use any other two vectors to form our coordinate system, as long as they have a 90-degree angle between them. In the language of linear algebra, we would say that these two vectors are orthogonal to each other. And since any other vector in the plane can be expressed as some combination of these two, then they form an orthogonal basis. If these basis vectors also both had a length of 1, then they would be an orthonormal basis. Something we can also do with vectors in the 2D plane is to form a dot product, which involves multiplying the components of each vector and then adding them up. We can do the exact same thing in 3 dimensions by just taking another component into account. Frequently, it's x, y, and z. But again, we can use any 3 perpendicular vectors as a basis. In fact, not only do these concepts naturally carry over to dimension 3, but they can easily be applied to any finite dimension. What a Hilbert space is then, is the extension of these concepts to an infinite number of dimensions. And instead of just ordinary vectors that are arrows in space, the vectors in a Hilbert space will also include abstract mathematical vectors. So they are things that live in a vector space, which is just a well-defined collection of objects that satisfy certain rules. The main ones being that you can scale vectors and add them together without leaving the space. So the set of all row vectors form a vector space, as does the set of all column vectors. More interestingly, the collection of all n by n matrices, and even of all functions, form a vector space. Now before moving on, as things begin to get a bit more abstract, I'd like to emphasize that you should really always be keeping the two-dimensional case of arrows in space in the back of your mind. That's the intuitive picture. Everything else will just be a way to codify the same type of behavior in a more abstract general setting. In essence then, a Hilbert space is a vector space with 2 extra requirements. The first we'll cover is that a Hilbert space is complete. In order to understand what this means, I think it's very helpful to consider polynomial functions. That is, any function that can be written in the following way. The space of all functions that can be written like this itself forms a vector space, where a very natural basis to choose is the set of all powers of x. So any function living in this space can be written as some linear combination of these powers. Let's now consider one very specific linear combination. As we continue adding terms, the function should start to look more and more familiar to you. And in the limit of an infinite number of terms, this approaches the Taylor series for sine of x. We can take another linear combination to arrive at cosine of x, and yet another to arrive at the exponential function. But here's the thing, none of these are actually polynomials. Any polynomial has only a finite number of powers. It can be really large, but it must have some cutoff. By letting n go to infinity, in all three of these cases, we have ended up with something outside of our vector space. How did this happen? We were just combining a bunch of polynomials together, and then all of a sudden, a whole different type of function appeared. Well, something similar happens in a setting you might find more familiar. Consider the following sequence of numbers. Each particular number is rational, but as the limit goes to infinity, the sequence converges to pi, an irrational number. In fact, this phenomenon occurs in all sorts of places in math, and mathematicians have found a way to deal with this general problem. What's needed is to realize that in all these cases, the space that we're working in is actually part of a larger space, one that in a sense completes the smaller one. So in this case, the real numbers are the completion of the rationals. In the case of polynomials, its completion is the space of all continuous functions. The technical term that's used is to call these types of sequences Cauchy sequences. And if there exists a Cauchy sequence converging to something that is beyond the space, then the space is incomplete. But if you extend your space to include these limits, and now every Cauchy sequence has a limit that exists inside of it, you get a complete space. So a Hilbert space is a vector space that is complete. This naturally brings us to the second requirement for a Hilbert space, namely that it needs to have something called an inner product defined on it. A basic vector space has enough of a structure that allows for adding vectors and scaling them. But there's no notion of distance nor angles between vectors. This is a problem since, in order for the Hilbert space to be complete, we need to find Cauchy sequences and determine where they converge to, a process which requires having some concept of angles and distance at hand. In order to be able to measure these quantities, we need to add some additional structure to the vector space, an inner product, which is a function that satisfies these criteria for any vectors u, v, w in the vector space and numbers a and b that you're scaling vectors with. Essentially, this is just a generalized dot product. It is a way to capture the lengths of vectors as well as the angles between them for a general vector space. In fact, in the case of the familiar 2D plane or 3D space, the regular dot product just is an inner product. So a Hilbert space is a vector space that is complete and has an inner product. Or to put it even more concisely, it is an inner product space that is complete. What are some examples of Hilbert spaces? One example is just the straightforward generalization of Euclidean space I mentioned earlier. It's the set of all sequences where this infinite sum converges. The inner product between any two vectors is just the dot product, but with an infinite number of terms. And from an inequality that's valid on all inner product spaces, this guarantees inner products between any two vectors will converge. Another very important example is the set of all functions defined on the interval 0 to 2 pi, where this integral is finite. This requirement guarantees that the following inner product is well defined for any two vectors in this space. And if you focus on these trig functions, the inner product between any two different sine and cosine functions is 0, which means they are all orthogonal to each other. Amazingly, they form an orthonormal basis for the entire space. So they can act as a sort of coordinate system here. And any function in the space can be written as a linear combination of them, leading directly to the Fourier approximation of functions. Yet another extremely important example is Schrödinger's wave function in quantum mechanics. The wave function is what describes the state of a physical system, and it lives in a related Hilbert space, this time defined over all real numbers. Interestingly, if this is the run-of-the-mill Riemann integral that most of us are more familiar with, then there will be sequences that converge to something outside of the space. In order for this space to be complete, and thus actually be a Hilbert space, the integral here needs to be the more versatile Lebesgue integral. A huge thank you goes out to this video's sponsor, Brilliant.org. I've been studying math and physics for years. Along the way, I've learned that the best way to solidify my understanding is by doing tons of practice problems. With Brilliant, you'll never struggle to find engaging problems to work through again. Packed with thousands of lessons spread over hundreds of courses, each lesson provides opportunities to interactively play with problems, allowing you to test your knowledge as you go. Not only will you be able to finally develop an intuitive grasp for calculus concepts, but Brilliant gives you the opportunity to explore topics like quantum mechanics, machine learning, and even mathematical logic. If you'd like to try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/abidebyreason or click on the link in the description. You will also get 20% off an annual premium subscription.